So people told me that Jack and I gave a little too difficult talk, and therefore it's very hard to follow. And I would then say that there's a paper I wrote, Non-Vanishing of Integrals of mod P-modular forms, that will appear the review volume of the 2022 conference here. And that section 6 contains what I said, basically the first lecture. So you can take a look. Section 6 only. The other part is the lecture on that conference. You can sort of ignore. Okay. So now I go on to the proof of main conjecture. The main conjecture is, of course, the Katz periodic L is equal to Iwasawa power series of anticyclotomic main conjecture for the branch character. Branch character anticyclotomic. Hi, and we write this as a psi minus projection. That means psi 1 minus c. Then the idea of proof is just there's a kind of middleman. It is called the congruence power series of branch character psi. It's kind of strange that starting from chi, you lifted something. This is not unique. However, this guy is actually basic up to unit only depending on chi. And Jack told us that he doesn't know that it is really anticyclotomic or not. It is, of course. And I never proved it. It's so easy. But I mean, I know that from the first. But anyway, so this H psi is the characteristic power series of the Selmer group of adjoint of induced representation. So the adjoint, you let two-dimensional representation acts on the real algebra of SL2 by conjugation. So that is called adjoint. And adjoint of the induced representation from M to F of the universal character Jack introduced. That Selmer group, so this guy actually is just split into this way. Direct sum induced of anticyclotomic projection of psi minus. So the Selmer group accordingly split. Okay? And this the characteristic power series of this is just this relative class number. And this should be L minus P related to, because this psi is a universal deformation of psi modulo P, right? So that this psi minus is reduces to chi. So this is the universal anticyclotomic guy. And this has to be this. That's the Iwasawa's conjecture. So this is Selmer group of this in Fm psi minus that we are studying. And this characteristic power series is F, I wrote F minus. Okay? So this is therefore product of, this should be product of this LP minus and this one. And what I proved last lecture is HMF L minus P divide this guy. And this guy is equal T theorem of Fujiwara, HMF F minus. Okay? You see, this R equal T theorem solves the Fermat's last theorem or the Shimura-Taniyama conjecture, or whatever modularity conjecture. it's not easy to explain. It takes about perhaps 1 year lecture or something. And so I just assume this thing. And so if I could prove this is an equality, then I can cancel out and I get this. That's the anticyclotomic main conjecture. It boiled down. Also, I explained in the last lecture that to prove, therefore, I prove H psi now divide the other reverse minus. And by reduction process, you take modulo P over the arithmetic prime of weight I naught. Yeah. And you just take its value at P, divide, this is just a constant, it doesn't change anything, LP minus at evaluated at this capital P. This I try to prove today. Then coming back here, it will implies reverse divisibility. So you get an identity, and then I cancel this HMF. That's how things goes. And actually, this was boiled down. This boils down to show that the certain inner product, so big theta is the universal sort of the family of branch character chi, and then you reduce modulo P. This lives in weight Si0 space, usual finite dimensional space of modular form, that's a CM form. And last time what I explained is that this times F, or the entire, so this space I just wrote, actually this is maybe SW, that I just write S. It boils down that this guy divided by the canonical Néron period is in actually W. And this implies this that I explained last time. Okay? So that's the key point. On the other hand, there's a so-called Shimura series. You want to show something is integral, periodically integral. Only things you can imagine is that you just somehow you create, so you pick anything here, some modular form F here. So the theta F divided by omega 2I is in W. That's the question. Only things you assume is that this is a CM theta series. This has a cusp form in the same space with coefficients in W. And the only things you could do is that you just try to find a modular form, phi. You evaluate at the CM abelian variety, so X of some CM abelian variety, X of CM abelian variety of the lattice. A and B is the lattice in M. So and this phi is a modular form 2 variable, and if it has a Fourier expansion whose coefficients all in W, then by Katz theory automatically this value will be in W. So I need to find this guy to show. That's the old question of Shimura, that Eisenstein series, as Jack explained, you plug in this kind of, it's a one variable in that case, plug in this kind of CM abelian variety, then it produces partial L value of Hecke L function. And in that way, you know Hecke L function is integral. So Shimura long ago asked me that you have some L values which behaves just like Eisenstein series. At each CM point, you give yourself this kind of period. And you have quotient, so the algebraic part of the L value, and you have infinitely many of them. And is there any way to find a modular form which has that value for the assigned point? And Shimura found such kind of things for the ranking product. And that's I call it Shimura series. Okay, so but for the ingredient to find this, I actually need to write F to be a linear combination. There's some limitation, of course, of theta 1, theta 2, here of theta is, so this is weight 2, so this is weight 1 and 1. Okay? And all this has coefficients in, two expansion coefficients in W. If you could do that, then out of this data, I could construct similar series. And its special value you plug in, you get a ranking L value. And actually, this similar series has a pole at S equal 1. And the ranking product has a pole at S equals 0. And this S, there's a shift of this S variable, and they match. And the ranking product, residue of ranking product is this kind of inner product. Huh? That's also basically due to Shimura. And that means residue of that Shimura series is the one I want. Okay? Omega is a period of this CM abelian variety, but actually it's the same of OM is fine. Neron period of omega, or of XCM. So this complex point is C to the sigma modulo OM to the sigma. That's the Katz normalization of this period. Okay, so I need to express every form in this kind of way. Is it possible? This is the weight 1. Actually, I take the theta series of imaginary quadratic field M and normal form. You make a product of two theta series of positive definite things. Then this is a two-variable quadratic space with respect to F. I mean, it's a quadratic form of binary quadratic form of two variables. And then you make a product. It becomes a four-variable thing. Four-variable thing is a quaternionic, essentially, quadratic form. So how I do this is that first I write F to be the sigma of thetas, and this is quaternionic. Then you split four variables into 2 and 2, and you create this. That's the idea. Okay. So for that, I need a Jacques-Langlands correspondence. I explained yesterday, I think. So I explained the space of corresponding cusp form SB of A. This is just a made of functions from B cross over BA cross over our level gamma hat 0n and B infinity cross, or maybe I just don't do that, just a function into A, such that if you multiply any U in gamma node hat n, you get an appropriate Neven character. It's actually A, B, C, D goes to M over FD under suitable assumption. and psi of D. You see, psi is a Hecke character of quadratic extension M. But this ABCD is a matrix in GL2 of F idealization. Okay? So you just restrict it. And if you make assumption, good assumption, then it becomes like that. Also, if you multiply central element, then this character show up, this character omega Z of F, Z center. That kind of space. A is any ring because this is a finite. I mean, essentially modulo gamma hat n, if you make a right quotient by gamma hat 0n, it's a finite set. So it's just basically any ring, okay. On the other hand, I have this S, I can also plug in A. So Si0, it is weight 2 actually, level gamma node hat n, and this epsilon, and with coefficients in A. So this is corresponding object. And then the Jacques-Langlands map exists. It's not unique. Remember that B doesn't ramify at finite places. So therefore, the finite are there. BA, finite, is identified with M2, FA, finite. Yeah? And so they have the same Hecke operator. And this has a property, JL, you apply Hecke operator Tn, ideal Tn is Tn getting out of JL. It's commute with all Hecke operators. And this space actually spanned by all new forms. So it's a Hecke operator acts semi-simply over C. So the Hecke algebra is a reduced algebra. Okay. So out of that, I have this F. I want to write this F into first this way. I pick F. So I pick F here. So what I can do, I just explain the Fourier expansion, or Q expansion of F. That is something, this is a Adelic thing, Adel norm, summation psilon over F. Actually, it's a cusp form F cross. And A psi dy F Q psi. Yeah, Q psi is what? Q psi is just a additive character EF of square root of -1 psi y infinity EF psi x. Yeah. EF is an additive character from FA modulo F into C cross, and it's at infinity is just an exponential 2 pi I summation over all embedding into C with the total real, but X sigma component. And that I just write Q psi. This is far simpler than writing this kind of way. So this is basically a Whittaker function at infinity, this kind of thing. Okay, so this is an A. So this D or hat is then you take intersection, is the difference of F over Q. This is called differential ideal. And the word differential, you can't find out in the dictionary. That's a Bayes creation. And Xi is just element in F, and A is just a function from O hat intersected, I don't like to have a finite ideal cross to C. And it's a Fourier coefficient. It's just a function of ideals, integral ideals. Actually, it's a function of integral ideals. I mean, it's invariant of the units. This is a simple Fourier expansion it has. And this gives you kind of the theory of Hecke that theory of Hecke is something like that. So Jack created a nearly ordinary big Hecke algebra. Nearly ordinary. Then I reduce its modulo this capital P with 2 prime, 1, 0 prime. I get HP. This acts on SW. Yeah? By Hecke operator. This is generated by just the ends over n on this nearly ordinary. You have a projector to the nearly ordinary part for this kind of periodic setting, and the HP acts on it. And Tian, also nearly ordinary projector, commute with Tian. All right. Then our important thing here is that we have two pairings. Hecke equivariant. One is, I call it diamond bracket. It's no. Yeah, diamond bracket. Well, why not? I just do it. Use your parentheses. From HP times SW, having values in W, and you have a Hecke operator here. You have a function here. It goes to the first Fourier coefficient of F applied H. You plug in that Fourier coefficient, the Q expansion coefficient, the ideal psi, this is just a function. This is a function on this guy. And of course, this group has, this monoid has 1. And you plug in. And the marvelous thing basically Hecke proved is that this pairing is a perfect pairing. Perfect means just the home, W linear home of HP, W is isomorphic to S, W. And you plug in SW, then you recover HP. And that's funny, you have just a linear form phi, then you have a modular form here. That modular form has Fourier expansion. Maybe that modular form f of phi I write. Then its coefficient ay f phi is ty no phi of ty. Y is the ideal, integral ideal, so you can identify it with integral ideal, n I wrote. And you just plug in this Hecke algebra ty here, and then you evaluate, then you get a Fourier Q expansion coefficient. And this is isomorphism. It's a marvelous thing you have in GL2 theory. This kind of things are never true in other groups. Okay? There's another pairing. There's another pairing. Now SB thing, whether B is up or down, I don't remember. Yeah, down. SB thing, SBA times SBA is just, I put bar here. Just means you have an even character, epsilon comes out, you multiply U, inside from the right. This epsilon, you put the bar here, this is a finite order character, you get the epsilon inverse. So it's a Levin types becomes epsilon inverse if I put bar complex conjugation. So if you have a F and G, then this product, Fg is a function of SHB, that is B similar variety, it's the point set. And why not? Then you integrate over HB of the product. This d mu is a measure of volume 1 on gamma hat node n. But you see, this gamma hat node n, if you have a B cross, I forgot center. This B cross intersected to gamma node hat n. It's a finite group. Modulo center is a finite group, gamma bar. Actually, so therefore, I just take a representative set A. In other words, there's a finite set, and this is just a union of B cross A, gamma node hat, and so on, finitely many. Then, for example, if you take A inverse here, gamma A is a finite group, and the order of this group, I write EA. What I'm saying is that for this coset, B cross over B cross A, gamma hat 0n, and so on, this kind of idea, divided B infinity cross FA cross, this guy acts, right, by conjugate, because I conjugated A inverse here, multiply from this side, this guy acts. So this gamma hat thing has volume 1, but actual integral, you need to divide image. Integrand is actually, volume has 1 over E, so it is just a summation, 1 over EA, FA, GA. So this is it's far more easier to write this, but this looks like Peterson inner product. So this is again perfect. By the way, I assumed F over Q and ramified at P. And then actually, and P bigger than 5, then the E doesn't divide EA. So as long as A is something like W, it's perfect. Or any periodic valuation ring. It's just an elliptic point. So in the case of Q, quadratic extension containing, imaginary quadratic extension containing roots of unity is only root of fourth root of unity or sixth root of unity, that kind of things I'm saying. Okay. Then you have this two pairing. Okay. You have this two pairing. I have this. And so you can take this to be Heike operator goes to this pairing. Also, I write bracket thing. And if apply HT, then you get you get a corresponding form that I write, say, a theta of F tensor G. Here you get F applied T psi dy G. And this pairing is Hecke equivariant, so you can bring this to the other side if you want, whichever side you can put. And so this is, I'm saying that this is the theta series. Why? You remember that this monoid which creates the delta hat A, B, C, D in M2 O hat. At this moment, I think this is BA finite part. That determinant is in FA plus, and A, B, C, D is in O hat, no, N part, N completion plus, or rather no condition, but determinant non-zero kind of condition there. And I wrote this as a disjoint union of Tn's for integral ideas, whose determinant basically this N. Huh? Theta of F tensor G. This F tensor G, you should have asked slightly earlier. I erased everything. So if I have a linear form phi from HP to W, and for phi, I take H goes to F applied Hecke operator and G. Then you have a modular form whose Fourier coefficients at Y, this is a phi, so the F phi is A of this value. Y G. So I plug in. This means that. Okay. So, and you remember that this Hecke operator, this Tian, is just you write down disjoint union of alpha gamma hat n, and then the FTN is just a summation epsilon inverse alpha. Of course, this epsilon extends to this group because I have this guy there. F En x is F x alpha, something like that. And you just, so it's basically it's running over all this. And having values, you move this. That means you have support function supported by Tn. And then you just go around all delta. So this is actually, simple calculation shows you that this one is summation A and B. You remember this is a complete representative set of SHB, similar variety, of epsilon inverse, A inverse, no, theta, EA inverse, EB inverse, theta AB. What's theta AB? I already. What's theta AB? Theta AB is just is a theta series summation xi running through A delta hat B inverse intersected B epsilon inverse the Neven character A inverse xi B. Because you multiply A inverse xi B to element here, you get something in delta hat, so you can apply epsilon. Okay? Q xi, or maybe EF. In the classical language, norm xi z. This is a classical form, not a deric form. It's a theta series. Right? Because Hecke operator brings A component of this guy to some B component there. So the action is A alpha B inverse. And it's running over all delta at xi. But you have an overlap of this EA amount, so you need to divide by that. But I said that this is in W, so you don't worry. All the time I use that F is F and G doesn't disappear. This is just I take F and G. I forgot. One thing I forgot. FA, GB. Because it's a kind of product. Okay. So that I succeeded writing this way. Now I try to split it up into two pieces. Why? 11:15. Oh, I have a lot of time. Okay. So I fix the representation M going into B. M is a CM field. This is definite, but nowhere ramifying at finite place. So any CM field can be embedded into B. Okay, so this embedding, say, rho. Then you let M tensor M over F acts on B by V goes to rho A, V, rho B, T. So this is the A tensor B, V. On the other hand, this is M direct sum M. Okay. So you apply idempotent of left side, idempotent of right side you apply. By this fact, B is splitted into left guy and right guy. L is isomorphic to R, isomorphic to M. Actually, strictly speaking, L is this B times 1, 0, or maybe this is a left action, 1, 0, V. How you can say there's a, so if I write this, you see this two-dimensional, this is four-dimensional. Therefore, B is M tensor M times V. I just fix a generator. And in good places, for example, if M goes A, this guy is something like A a complex conjugate or something like that. This happens, for example, if you localize at some prime q, and if mq is fq direct sum splitting prime, then you can write this way. Then this b is something like 1, 1, 1, 1. And the left component 1, 1, direct sum 1, 1. Oh, stupid thing. But this choice is very good. It's very unit. Okay, so therefore, you have that epsilon is the Brucher function. The Nevin character is a Brucher function here. Or, so this is a, in adelic way, this is a theta series, theta of epsilon inverse, or something like that, in adelic sense. Yeah? All right. Then you, over the Adel, you adelize it. BA finite is LA finite, direct sum RA finite. And you have this epsilon inverse function supported on epsilon inverse. Then it's a kind of exercise that you can write this epsilon inverse a finite summation of phi L part, phi R part, phi L finite summation this way. These are Brucher function of this side. This is the Brucher function of that side. And this is out of that, you create theta series. And if you choose this generator well, something like that, then this is integral values. You can make with these two integral values, W values. Okay? So this is how I achieve this splitting. So this, because this is adelic things, if you go back, you need to go back to classical things. So theta, say phi something is actually on the GL2, maybe I should say SL2 of FA, automorphic form of weight 1. It's a classical way. SL2 is, but if you do it for GL2, SL2, you have a strong approximation theorem hold. So there's only one form classically. But here you have a bunch of that you get. And that makes things, of course, I need to work with GL2. So it's fairly complicated things I'm doing, actually. Okay, so Shimura series. What is Shimura series? That's the kind of worst part. If something Shimura invented, and if it is very original, then it's very hard to understand. And he never explained the motivation of his definition. He just give yourself. And I once asked him that, what is the motivation of this funny definition? He said that magician doesn't disclose your trick. Okay, so I don't know how he comes up. But anyway, I just so you have a Z and W, say upper half plane. And you define EZW to be minus Z1 column vector. Then you multiply W1 and then 0, minus 1, 1, 0. It's a 2 by 2 matrix. This is something like that. And of course, you can do tuples, ZW, H to the I, Hilbert modular case. You just consider PZW, just a tuples, PZ sigma, W sigma, sigma I. Then this stays in M2, F tensor QC. Okay? And this is the quadratic space you are thinking, M2F, determinant quadratic form you look at. And this funny function, oh, by the way, as you know, alpha 2 by 2 matrix Z1 is alpha Z, linear fractional transformation J alpha Z, right? If alpha is something, something CD, this guy is CZ plus D. Generalization of this to all classical group, Shimura created in his old paper of the classification of abelian variety, 1963 paper, over complex numbers. And so for him to come up, this is kind of stupidly easy thing. Using this kind of higher dimensional thing, he created a family of abelian variety, his PEL type abelian variety over C. That's the start of investigation of Shimura variety in 1963. That paper very good, actually. Rare paper of Shimura, you can read it well. And it's amazing rarity it has. Anyway, so by that formula, if we 63. It's not Shimura variety, it's I forgot the name of the title of the paper, but it is in Annals. And it classifies all PEL type abelian variety families over C. Shimura variety is over reflex field. So he started from C.
That conference was in 66.
Yeah.
Where I think Shimura variety is very
Yeah. That's, so within 3 years, he did this kind of stuff. Okay. So if we have 2 by 2 matrix, say GL2 something, maybe F infinity, then obviously alpha P ZW beta iota main involution is P alpha Z beta W J alpha Z J beta W. And now I define V is again this M to F tensor QC. To be trace of PZW V iota. This is in CI. Yeah? All right. Oh, each component of this, or sigma component of this, is degree 1 spherical harmonic of that quadratic space M2F determinant. And then you have, by this formula, you can easily check alpha B beta iota ZW is J alpha iota Z, J beta iota W, V alpha iota Z, beta iota W. Okay. He defined this kind of things in his 1981 paper for all quaternion algebra. In 1984 paper, basically all orthogonal group which produces similar variety. And the later paper, I forgot the time, all unitary group, whatever. And it's a kind of increasing difficulty. And how you can say, first paper hard, and then you get lost, and all that paper, and nobody understand. But it's I don't think he has any error in it. It's something like Japanese bullet train. It runs every 7 minutes, never delay. I took a bullet train from Tokyo to Sendai just last April. It's delayed 2 minutes. And the conductor apologized profusely. And she wrote the paper, something like that. And okay, so I define Shimura series H Z W S is sum over not zero, determinant zero, okay, M to F modulo U. U is a subgroup of O cross finite index. It's a stabilizer of all terms of H. And so I'll give you a term, Schwarzbrucher function of this M2F plus finite, not Schwarzbrucher, Brucher function. And alpha, you pick cusp form F, cusp form, Hilbert modular cusp form of some weight. But for me, it will be weight 1 form, but it doesn't matter. Then you plug in its Fourier coefficient, but it's a classical form. So its Fourier coefficient is indexed by the element of F, determinant of epsilon alpha. It's a funny thing here. Epsilon is minus 1, 1, something like that. Fourier coefficient determines the Fourier coefficient of this one you pick, and alpha VW to the minus I, the same thing, minus 2SR. Here, here, the alpha VW to the some K is sort of a sigma thing, then this is just a product of alpha VW K sigma. And I is just a summation sigma over all sigma. And of course, this is negative. This is never zero, actually. This alpha ZW never zero. As I said, this is obviously any weight is fine just for definition. But for me, it will be weight 1. And wait a minute. Don't go too fast. And so, as I said, this V goes to B, P, W, ZW is a spherical harmonic. I wrote this kind of thing. If you watch this, and if you feel this is not a Hilbert modular form, you'd better quit mathematics. As long as it converges. So ZW is spherical harmonic, and ZL long ago, it is actually quadratic form, symmetric bilinear form, PZW, and the determinant of PZW is 0 by definition. It's vertical one, horizontal one, and then this is a spherical harmonic. And in fact, it lives in scalar extension C of minus signature space, because the M2F is signature 2, 2. So that has quite a meaning. And then Shimura proved that this converges on the right half plane, continued meromorphically to entire SC, and first pole towards left is at S is 1. So actually from the 1, it's holomorphic. And there might be sporadic poles. And as I said, if you plug in some, this is a kind of, depending on S, it is a, if you insist Hilbert modular form to be holomorphic, it may not be, but it is certainly the automorphic form of mass type for any S. And this kind of form exists, as I said, any orthogonal group or any unitary. Okay, now I evaluate the thing, and this is easy, but if you honestly, I can do that if time allows, but I just write it down. So I now pick, so I am, now I'm in M2F, not B, okay? My original argument started from B and created the expression of theta 1 times theta 2 kind of things for given modular. Now I'm using M2F. That. So in 1981 paper of Shimura, we can do that for any quaternion algebra D over F and reduce norm pair for this kind of series. Then you need to replace everything M2F appears, it will be B. But still, you get, in that case, quaternionic automorphic forms. So at the very end, what you get, it's a nice exercise that you actually evaluate this one. So I consider 2 points Z0, W0 inside M intersected HR, pair of plane. Then I define Z0, Z Z1, you type multiply A in M, that means you multiply A to Z times A, 1 times A. Then you have a 2 by 2 matrix, Z0, 1, row, because these two are linearly independent of 1. Row from M into M to F. Do the same for W, 0, then you get R from M going into M to F. Okay? And then you split again using, so this M acts on M to F, just A tensor B, V is row A, V R B C, something like that, the same way. Then you split this into two pieces. Okay, so the formula is something like that. So again, this, now you assume that this phi infinity will be the tensor product. By that, I still use the same notation, but by doing this, I again have that M2F is M direct sum M. And this is positive definite, this is negative definite. I arrange. And then you have a phi Schwarz-Brouwer function, I assume. This is phi L side, phi right side. So this component I call L, this component I call R. And the Schwarz-Brouwer function. Of course, any Schwarz-Brouwer function is a linear combination of this, so it's sufficient to do this. Then, suppose this Z node produces CM type sigma. In other words, Z0 has those indexed by sigma I. But that is because this is in M, it is just, maybe I should say just nu. It is Z sigma Z0 for one guy. Sigma restricted F is nu. You can write this way. And this set of sigma is a CM type. Okay? Then I still have some time. Yeah, okay. This H evaluated. So you saw the definition, so I just erase it. So I plug in Z0, W0. Then this is ranking product of S minus 1 of theta of not L, phi prime L, and F prime. What is theta phi prime L? Is alpha, is alpha to the sigma phi L alpha V. I fixed the generator actually. This is actually M2F is M tensor M times V. So this is a generator. And that generator, I evaluated the generator. Or if you shift it by that, you just forget about that. And this is a harmonic, spherical harmonic of the M normal form. So this is the infinite part. And then exponential something, you get a Schwartz function. Okay? And so this type of theta. And F prime is theta phi r times F. Funny. So for this, then as I said, this has a pole at S equal 1. And this is normalized so that this D has a pole at S0. And the residue S is 1, so to make it 0, of this guy is theta phi prime L F prime. Okay. Now no. You just honestly compute that sum. It happened to pop up out of this alpha PZW, alpha ZW. And I said PZW is basically minus component. So if you, what's the definition of what? By infinity. I'm set it's a Brucher function. There's no infinite part. For the moment, any Brucher function. This kind of definition, nothing you impose. And out of this Brucher function. This guy basically produces alpha to the sigma kind of thing. Very tricky way. But it's elementary, surely. And so that's the formula. And I get, if you are interested in, you just read my anticyclotomic main conjecture, the paper 2006 documenta, and perhaps the 4.5 computation given. It's a stupid computation, but it's fairly long. And of course, that's a simultaneous computation. But if I write simultaneous computation in my way, it's far easier. However, it might contain errors. You have to be careful. Okay? So now I have a choice. This F, I have a freedom to choose. So I already write down your F to be summation of theta 1, theta 2, right? Then I just pick this guy to be theta 1, and this guy to be theta 2, and this guy so that this is big theta, ideal A component. This I'm working in GL2, so you see the adelic theta series corresponding to this psi p is again summation over ideal classes of theta A, as Jack separated Eisenstein series into pieces. And the same way, you can separate theta series into pieces. And this is a classical object. This is a adelic object. And that is written in this kind of way. You need to choose Schwartz function so that this works. All right. On the other hand, for this side, oh, I'm getting tired. You are certainly getting tired, I guess. Sure, it's too long. But 1.5 hours, without 1.5 hours, you end up here. And I can't prove anything. If I give 3 talks, then it would have been okay. But you don't really, yeah. So basically, residue S is 1 of H VWS has a Q expansion in the following form. Imaginary part of Z, I would kill all the junk terms. And it's all periodic unit. I don't care, actually, when you plug in Z0 and W0. If you choose ZW well, sigma alpha in gamma over M2F. Again, now gamma is in SL2F, which is this HSF S is modular 4. Det alpha, totally positive. Phi star, maybe phi infinity. This is a Bloch function, star of epsilon alpha. EF, determinant alpha times Z of F, weight 1 action of alpha W. This phi star is a partial Fourier transform. Partial Fourier transform with respect to A, B, C, D, A prime, B prime, C prime, D prime is EF, A, B prime minus B, A prime. Partial Fourier transform essentially preserves the W integral up to some Gauss sum kind of thing. And so if you start the W integral thing, you might have some Gauss sum popping up, but basically this is W integral. If you need, of course, assume that F is also W integral. But I will choose, as I said, F to be another theta series I found of theta 1, theta 2. And so they are, where I wrote that. I might have erased. Oh, this is theta 2, and this I make with theta 1. Right? And then everything goes. And I found the this is holomorphic. Look at that. This is obviously holomorphic. And I found a form which gives rise to Peterson inner product. And basically, this is the end of the story. So it's 15 minutes earlier. So it's actually, I'm giving only 75 minutes. You can't complain about that. And this is basically the end of the story. However, one thing I have to be very careful is that so I proved basically this theta, theta1, theta2, with respect to gamma divided by omega 2I is in W up to some Gauss sum. However, this gamma may not be gamma node n I started. When I write this original phi into summation of phi L tensor phi R, this has level, say, n. But these two guys has higher level. See, if you have a phi, say, for example, this guy is, say, characteristic function of, say some lattice. L is no good, some lattice L of your quadratic space. No, this is B. The level of the theta series is basically this L dual under the symmetric bilinear pairing. So suppose symmetric bilinear pairing has integer value in L, then you take its dual lattice, and annihilator of this is the level. This kind of things, the Hecke. And if you split, how you can split? Because you start from this basically delta hat intersection with B. And you extend a little to this to be the Eichler order, O hat, and O hat. Then this level is basically n. And then you need to split it to the two pieces m direct sum m because this you can't split integrally into two pieces. So you get further the level NDMF square even you choose this generator V very well. So this gamma has slightly more deeper level. But original sort of, then you plug in the summation thing. Then this getting down to the original level with, okay, so theta of summation theta 1, theta 2, theta 1, theta 2 is, this guy has original level. So it is gamma node n. So this guy and this guy has a difference that you need to add the gamma node n gamma index, right? This guy is in W, but if this P divides this guy, you have a trouble. And it's further worse that not just this, but what I need to do is a inverse delta hat B intersected B. These guys further add level. And you can choose by strong approximation theorem that these guys are just concentrated in B, 1 prime Q. So actually, you get almost the end of the story. Oh, I'm dictated by computer. So if you choose this, then the level is actually NDMF square and some Q to the high power M. You don't know, it depends on several of that. Then the index So this is something like A. It doesn't matter for gamma naught or something like that. Of gamma, of this part is actually principal congruence. Gamma, so I would say intersected gamma 2 to the m. The index, this doesn't matter because original n contains DMF. So the index is just a prime appearing in these guys, and that's prime to P, so you forget about that. But this has a lot of trouble. And the index is something, norm Q to the some power is prime to P. You choose Q outside P. And then you have a norm Q plus minus 1 kind of things show up, right? The order of GL2 of finite field, P plus 1, P minus 1. And this could be divisible by P. But F is unramified at P, so you can choose a prime Q, which is not divisible by P, as long as P is bigger or equal to 5. 3, no way. Mod 3 class is only plus 1 and minus 1. So I have to assume P bigger than 5. That's kind of caveat, and that's the end of the story. So now you can complain, it's too long.
Questions? So the original formula you wanted involved a Peterson product on the Hilbert modular variety, and you replaced by B, and you replaced by this parenthesis Peterson product. So do you mean that the Jacquet-Langlands isomorphism is isometric, preserves these products?
No, obviously, Jacquet-Langlands side of this is just a sum of finite summation of Fn.
Yeah.
And the other side is integral. So if both sides is kind of rational, transcendency is different.
Yeah, so what
doesn't make
no,
sense.
Yeah.
I mean, Jacquet-Langlands
is not canonical. No.
Yeah.
Yeah.
It's not one vector goes to another vector.
Well,
It's
here
a
it
representation goes to a representation.
yeah, but here it was.
But also Jack is
yeah, I know. But here it
scale it out.
But here there was a map.
But it's rational to rational.
Yeah, but then what you get here is a
No,
parenthesis.
Because the point here is that the change of quadratic space. I started from B, signature for 0, split it in 2 pieces MM, and created theta 1, theta 2. Okay? On the other hand, M2F, again MM, but signature plus minus. Still theta 1, theta 2 is that quadratic space.
So theta 1 and theta 2 are
Theta 1, theta 2 created by B.
But they are on Hilbert.
It's a Hilbert modular from weight 1.
Okay.
So you plug in to M2F, M2F, MM. It's again plus and minus, I said.
I see.
That I can plug in theta 1, theta 2 this side.
And the theta is always on the Hilbert modular side.
Of course, it's a theta series Hilbert modular form.
Yeah, but so there is no counterpart. You don't use a B counterpart of theta.
Huh?
Okay.
I mean, theta series is a metaplectic group, and theta series is a function of a metaplectic group, not the quaternion algebra, not the orthogonal group.
No, but it's well, okay. Okay, that's all.
Are there any further questions?
Is there a sense that the Jacquet-Langlands preserves some rationality structure?
It's preserved the rational structure if you, if you double it, so theta F tensor G, this is what? SB, W, both. But I need two guys. Then you get A F T psi d F d q to the psi, and this falling into S W. As long as, so this is a Peterson inner product on SHB, because this is an automorphic form on B. And it is integral. And this is integral in the Hilbert modular side. And this map is a unique. However, I need to double it. Without that, I cannot have this. That the main reason is that the Clifford group of B is basically the Clifford group B is B cross times B cross over the reduced norm. That's why I need two things. So the Jacques-Lang runs from B cross to GL2. But if you formulate it at this Clifford group to GL2, then it's unique and canonical. One exists.
Okay, any further questions? If not, let's thank Professor Hida again for